let's see. Well, why don't we get started? So welcome to the third part of this morning session. And the final part of our session will be on the topic of computing as it relates to agriculture, the environment, disaster, and food, energy, water. So really this is, you could think of this as, we started with urban environments, and now we're thinking about the relationship between computing and the natural environment, the natural world. We have three panelists, speakers and panelists for this session. The first panelist will be Robin. Well, I guess I should give them in the order we're going to present. So the first panelist will be Sonny Ramaswamy. He is he was appointed by President Obama as the director of the National Institute for Food and Agriculture. NIFA provides funding opportunities to catalyze societal changes as it relates to food and agriculture. He's held a number of academic positions, including the Dean of Oregon State's College of Agricultural Sciences, the Director of Purdue's Agricultural Research Program, and a University Distinguished Professor at Kansas State's Entomology Department. He's been involved in several federal grants from several different agencies, as well as commodity groups and industries for his research in the integrative reproductive biology of insects. He's published over 150 journal articles. He is a fellow of the American Association for the Advancement of Science and a fellow of the Entomology Society of America. So that's our first speaker. Our second speaker will be Shashi Shekhar, and he is a McKnight Distinguished University Professor in Computer Science at the University of Minnesota, and he is prominent in the area of spatial computing and geographic information systems. He is a winner of the IEEE Computer Society Technical Achievement Award and an IEEE Fellow. He has served on a number of national committees, National Academy committees. He is a former member of the CCC, who's sponsoring this meeting. And he most recently has co-organized one of the NSF Food, Energy, Water Systems workshops. And then finally, we'll hear from Robin Murphy. She is a Raytheon Professor of Computer Science and Engineering at Texas A&M, and she directs the Center for Emergency Informatics. She is an IEEE Fellow and does research in artificial intelligence and robot interaction, particularly as it pertains to disaster robotics. Robin wasn't able to be here in person because of a family emergency, so we have a short videotape of her talk, and then, as I understand it, she'll participate by phone. Can someone confirm that? Awesome, great, okay, good. So with that, why don't we let our first speaker, Dr. Ramaswamy, give his talk.
Okay, good morning, and thanks so much for the kind invitation to speak to this group, and also giving me an opportunity to share with you some of the things that are happening in the world of food and agriculture itself. And sharing with Shekhar here earlier, Dr. Shekhar earlier, that about 3 years ago, I believe, the Cyberphysical systems folks within the National Science Foundation had invited me to share some thoughts on this particular topic. And so at that time, I went through talking about Kevin Ashton's coining of the term Internet of Things, and then related it to food and agricultural systems. And we coined the term and the hashtag Internet of Agricultural Things, and because we invest quite a bit of resources in that area as well. And I'll share with you a few thoughts about why this is an area worthy of your consideration as members of this community, and people beyond you as well. And so with that, I'm going to go ahead and get started here and really share with you about 21st century food systems first, and why it is that we need to be thinking of smart systems that can allow us to achieve what it is that we're trying to do in regards to the 21st century food systems itself. And so I like to say that we have an existential threat. And this existential threat is nutritional security. And all of us, I think many of you in the audience as well, when we give speeches, when we write articles, or when we submit grant proposals, et cetera, we start off talking about the year 2050 and the impending disaster that we're going to have, about the population boom and the issues related to climate change, et cetera, et cetera, et cetera, and that something bad is going to happen in the year 2050. So we're all waiting with bated breath to see what's going to happen. Well, actually, it's happening right now. And this existential threat that we have right now is we have a population of about 7.4 billion people today. And today, the 9th of May, 2016, we've got about 850 million people across the globe that's going to go to bed hungry. And a consequence of that is 21,000 people will drop dead today. About one person dies every 4 seconds globally for lack of food. On the flip side of it, the sort of the yin and yang situation is that we have about 1.3 billion people tonight, before they go to bed, and many in the audience here will take Lipitor for cholesterol, high cholesterol. We'll take baby aspirin for heart disease, metformin for type 2 diabetes, medication for hypertension, et cetera. And as a result of that, today, globally, about 1,000 people are going to drop dead today because of excessive amounts of food, excessive amounts of calories, and sedentary lifestyles and all that. And in fact, Ursula Bauer, she's with the Centers for Disease Control, she did an exquisite study and says that 75% of America's healthcare costs, 75%, and as you know, that's the one that's been going up fastest, although the Affordable Care Act has pushed that slope down a little bit. And along with college tuition, healthcare keeps going up at a very rapid rate, about 3, 4, 5 times the rate of inflation. And she says 75% of that is attributable to chronic disease. Chronic disease such as cardiovascular disease, metabolic disorders, and things like that. And it is a result of genetics. And there's not a whole lot that we can do, although we're tantalizingly close to be able to even deal with it, but with these new techniques called gene editing. And we can actually edit the gene that contributes to the proclivity to becoming overweight or obese. And so we're not doing anything about that yet, but maybe in a few years we will. Along with that, she says, it's literally the amount of food we consume, the number of calories, literally the calories, and the quality of calories, and the sedentary lifestyles. A consequence of all this, her research suggests to us, and I'm sure you read about it all the time, is about a third of our adult population in America is overweight, another third is obese. And, by the way, if you look at children in America, a third of our population of children is, again, overweight or obese. And by the way, starting out in the late 1800s, every generation has lived for a little bit longer than the previous generation, to the extent that today in 2016, men and women in America live to about 80 years of age. Women live a little bit longer than men. And for the first time, children born in the first decade of this century will have a shorter lifespan than their parents because of the excessive amounts of food being consumed, the quality of calories, and the sedentary lifestyles as well. In fact, Ursula Bauer says you could be a complete couch potato and reduce the number of calories and improve the quality of those calories, and you could get to a better spot as well. That's the existential threat that we've got. And there are some significant opportunities for people like yourselves to become involved in trying to address this existential threat. And then when you narrow it down to this idea that we're going to feed, again, coming back to the year 2050, the projected population is about 9+ billion people. We're going to provide the food, the shelter, the fiber, the fuel, et cetera, for that population. And in thinking of how we go about doing this, there's a whole slew of externalities that are going to have an impact. So you've got the internalities, that is the food that we consume, the genetics we have, et cetera. And then you've got the externalities as well. When you combine those two, you get an interesting mix of things that are going on, everything from climate change to land and water constraints to ecological footprints, et cetera. All of these areas are primed for people in the world of, the kind of work that you end up doing, cyberphysical systems and computational efforts and things like that. Great opportunities for you to be able to become engaged in addressing these truly challenging societal situation that we've got as well. By the way, at the end of all this, We want to ensure that everybody's going to be healthy and happy as well. Therein is yet another opportunity for groups like yours to become engaged in this effort as well. So I don't want to leave you with thinking, oh my gosh, this is a really bad situation. We're going to be in deep trouble here with all the internalities and externalities. There is a path forward, and this path forward includes everything from transformative discoveries, such as the omics revolution that we've had, and in smart systems and big data and things like that, the enabling of our ability to ensure nutritional security is possible. Along with that, we've got what we very uniquely do is the knowledge that we're supporting that's being generated is not knowledge to be published in some scientific journal or in a book to be forgotten, and you pat yourself on the back and you got a paper in Science or Nature or whatever. No, that knowledge needs to be taken and translated into innovations and solutions and to be actually delivered to the end users. That's done by what we refer to within the food and agricultural systems as extension. This 21st century extension, there's some incredible opportunities. Again, the work that you do offers us some pretty cool possibilities, whether it's virtual reality or big data-driven possibilities of thinking of dealing with invasive species of insects and pathogens and weeds or other maladies that we might have as well. On to farming systems and education policies, regulations, and oh, by the way, communication aspects as well. I want to focus on just a couple of these items very quickly here in just the next about 5 minutes or so. And so really what we want, really the goal is to develop new or improved devices and products and systems. That's the bottom line. Within the agricultural production systems, we want smarter systems. And how's that possible? Ultimately, the intent really is to have sustainable approaches to ensuring that we're going to have health outcomes, and that results in economic outcomes as well, ultimately, is what we're interested in. And then there are a number of challenges. And unfortunately, as in many other parts of our economies, the food and agricultural systems are a crisis-driven enterprise. This crisis-driven enterprise, every day I get alert from from Homeland Security. There's at least about 40 to 50 stories in there on the alert. There's at least about 15 to 20 that deal with, you heard Chipotle had the problems with E. coli. They had the problems with norovirus. Or maybe there's an invasive species of insect that comes in, like the emerald ash borer, that's taken out just in the state of Michigan alone, 20 million trees, ash trees, just in the state of Michigan alone. Okay? These things keep coming in constantly. Oh, of course, the topic du jour is Zika virus and the mosquitoes that transmit them as well. So it's crisis to crisis to crisis, and on top of it, the abiotic considerations such as weather and droughts and climate change and things like that. All of this is contributing to this crisis situation. And what you do that allows us to be able to deal with this environment is to help develop the enabling capabilities to deal with these crises as well. Then you've got to have scale-neutral technologies, and last but not least is they got to be robust and stable and things like that too. So that's the context in which we are trying to do. I'm going to skip this slide right here. Oops. Okay, and we need smart systems for food production. Systems themselves. That is, the system is from the farm to the dinner table itself. And, whether it's the drone technology or all the omics, the genomics and metabolomics, et cetera, that are all part of this enterprise as well, they're all offering us unbelievable amounts of data and trying to understand the impacts of biological and non-biological stressors that impact our ability to achieve nutritional security is an area that we are I guess I kind of pointed over there. And so what we're doing is really in considering what happens in the world of plants and animals is this enterprise we refer to as genomics to phenomics, or genomes to field. That is all the knowledge that we've gained over the last few years in the world of all the omics-enabled capabilities that we've got. There are things that are going on below ground, above ground, and this generates unbelievable amounts of data. And the sensors, millions and millions of sensors that are present, All of this needs to be brought together in helping us. For example, if you're from the Midwest, if you're from Kansas or someplace like that, I'm sure you've seen where you've had lots and lots of rainfall, and the wheat that's growing out there is flooded, almost like a rice paddy. And in another 2 or 3 weeks, that is going to dry out, and you're going to have a drought. Okay, that plant, that poor little plant, is sedentary, can't get up and walk around like you and I do in case of bad weather. It's stuck there. In that flooding to extreme drought and heat, it needs to do what it needs to do and make sure that it provides our food as well. There's some very interesting possibilities to think of when it comes from your perspective in regards to smart systems and things like that. They generate lots and lots of data, of course, and along with that data, there's an incredible number of opportunities, and probably some of you know about the Cochrane collaboration already. If you don't know it, check it out. Ian Chalmers is the guy that came up with meta-analysis as an endeavor in the medical field, and it offers up some really, really significant possibilities of thinking how we might be able to enable us our ability to get food on the table, that it's healthy, and it enables us all to have ultimately positive health outcomes as well. I'm going to skip that. There's some significant challenges, of course. Ownership, privacy, et cetera, are all things that we're talking about, that we provide funding for. And it is literally from the farm to the table is where we're at. In fact, if you look at this in the entire supply chain from the farm to the refrigerator and your dinner plate, as well as your garbage can, we need smart systems in every one of those, and there's incredible amounts of data that we continue to get in there. I'm going to skip that part as well. Very quickly, a 21st century farm. It's not your granddaddy's farm anymore. There's lots of sensors there. Literally, an average farm has several thousand sensors on it, detecting nitrogen levels, moisture levels, insects, pathogens, weeds, etc. We provided funding for robots that run around looking for, they can tell the difference between a weed plant and a plant that we're interested in. They got onboard sensors, and they're taking all this information and then deploying either a laser to zap that, whatever that weed is or insect is or whatever it is, or deploy a drone to come in and spray only in that particular spot for us and not waste all the pesticides and other things that you might have, contamination of water. And these are actually now being sold by Monsanto and John Deere and other companies as prescriptive farming, using big data and analytics and genetics all brought together in an exquisite possibility. This young farmer, his name is Randy Dowdy, he grew 2 years ago 503 bushels of corn per acre. That's unheard of. The average that year across the United States was only 171 bushels. It comes about because of the kind of work that you do, is pushing as much as possible in regards to the analytics and those sorts of efforts as well. We partner quite a bit with other agencies, particularly with NSF and NIH, and we need for you people like yourselves to get into this enterprise, to think of real-time data analytics and controls that we need as well. And we have offered, my agency, NIFA, has funded a number of these enterprises across the United States in regards to the cyber infrastructure and tools and software and things like that that we've got as well. And I'll leave you with this last slide. Our Agriculture and Food Research Initiative is our, flagship competitive grants program, and within it, we have a number of possibilities for you. If you were to go to nifa.usda.gov, you can find all the information about funding opportunities we have. And the very last line in this is our partnership with ARPA-E. And a lot of the funding that's been provided by NIFA and by NSF, for example, is resulted in where ARPA-E is leveraging the knowledge as well. So I want to leave you with that, and thanks again for having me here, and I look forward to the conversation in just a few minutes.
Thank you, Dr. Ramaswamy.
So this is a very tough act to follow. I think we have the big picture from NIFA, and food is one of the biggest challenge. So what I'm going to talk about is in some sense complementary, and there is this new topic called food, energy, water nexus. And in this new thinking, people are saying that you can't just solve one problem at a time. If we just focus on food, sometimes problems arise in other areas. In my own, in terms of lens of color, so I come from GIS and spatial computing, and that's sort of my background. So let's first look at, where is this nexus coming from? So this is showing you the United Nations Sustainability Development Goals relating to the opening keynote speak. And there are many different goals that United Nations has set. This just came out last year. And within this, you can certainly see food, energy, water. Those are showing up in this area. But again, if you think about this diagram, possibly because of simplicity, each of these topics are shown separately. And we also heard early on in many cities, the departments are organized separately and silos decisions are made, which is in some sense are also happening at government level. But those often lead to other surprises. And here are some examples. I think opening talk, we heard about all the fertilizer washing down Mississippi and creating a dead zone in the Gulf. But there are many other examples. Similar situation is in Great Lakes. And this is showing you the toxic algae, which essentially shut down the water supply to the city of Toledo. Okay? There are other issues. If you actually go to Central Asia, this is a very large lake, similar to one of our Great Lakes. And because of cotton farming, it has dried up. Just very little is left, right? So these are some side effects. If we don't think about the impact on water and so on, other things happen. This is one other example. Actually, about in last 10 years, in order to attain energy independence, there was a lot of biofuel subsidy, right? And we were encouraging that. And that ended up shifting production from food to fuel, and it led to a lot of food price rise and riots and so on. Many say that this is what triggered the Nexus thinking. So many organizations like World Economic Forum and so on, they came to this thinking that we need to start thinking about these interactions. And it has become a national priority within US. You can actually see reports from many different places, Department of Defense, and now there is a NSF USDA initiative. You also have other agencies involved. Okay? So in this world, we think of things interconnected. This is sort of like systems thinking. It's not, saying don't focus on just one thing, but look at pieces together. And at least three pieces, food, water, and energy, are thought of together. And in systems thinking, we often focus on the interactions. So if we are going to grow a lot more food and we are using fertilizer, then we have to worry about that it actually takes a lot of energy to produce the fertilizer. And some of that may actually wash off to water and create water quality problems. So we need to study these interactions, have the understanding, and deal with them together. Okay? Now, these interactions actually have both positive and negative side. So we focused on the negative. But positive part is that if you can actually solve one of these three problems, it helps reduce scarcity and solve other problems. So these are the positive part. And efficiency is one way where things like cyber-physical system has come in a big play, and I will show you some example. Right? Now, of course, the world doesn't end with these three concerns. Okay? These three are also affected by other contextual things in the systems world, and at least three of them have been around. Previous talk, we'd heard about population growth. It's being projected that by 2050, we'll have 30% more people, which means we'll need a lot more food. But then in order to produce that, the constraint may come from water and so on. Climate change, as well as rising on economies, are other stressors. So essentially, we are looking at the systems thinking and understanding the interactions. So let's actually see what's the role of computing. Is this completely just an application? Has computing, is it a first-order solution or not? And there are many success stories. In fact, one we heard already in the form of precision agriculture. So this has been out there for almost now 2 decades. And as you can see, this was a reception just a year ago, and they were highlighting technologies like global positioning system, GIS, and sensing. CRA was part of this reception. So in this world, essentially, they do a very fine-grained mapping of the farm, roughly 10 meter by 10 meter grid. And you can think of soil sampling, understanding the quality of soil at each place. And then later on, when you are putting in seeds and so on, then you customize it to the soil. The amount of fertilizer is customized to the soil quality. So if the soil is already rich in phosphorus, we don't need to put more phosphorus, which means loss of money, as well as potential of runoff, right? And then, as I said, later on, the yields are also mapped, so you can actually connect and build a model of different farm practices to increase yield. And we heard that yield went up almost 3 to 4 times if you did it well. Okay? But it also actually reduces the runoff. Okay? So in this whole enterprise, which is sort of certainly a success story, computing has played a key role. You have all kinds of things, from sensors and control systems to data and so on. So this is certainly a place where computing has played a big role. Another place is the farm level. We just heard about the prescriptive farming. In fact, Climate Corp was founded by a couple of people who left Google, and they looked at weather data, and they were hired, I believe, by USDA to help with the insurance policies based on the seasonal weather. And then it was bought by Monsanto, which has rolled out this advisory. So any farmer can essentially hire this, and based on the satellite imagery and the weather predictions, as well as the local soil quality, they give advice in terms of how many seeds to place in each area. So this place, maybe not many seeds are useful because the soil quality is not as good, whereas here you may put more seeds and so on. So again, great commercial success, and in fact, this is not the only effort. There are many other startups in this area that are happening in the last few years. Now, this actually goes one step further. Another big success story, which has not been in press as much, is actually a global agreement called GeoGlam Global Crop Monitors. How many of us have heard of this effort recently? Okay, few of us, great. So in this, actually, many countries of the world, certainly G8 as well as MIS countries, they have come together to track 4 crops, maize, wheat, soybean, and rice. And they essentially, through satellite imagery, they are monitoring it every week or 2. So as soon as you have a risk of crops not doing well in any one country, they are able to start taking decisions about supply chain and making sure the food prices don't go up. Okay? So another success story of remote sensing, as well as machine learning and different kind of information sharing. So we could kind of say, well, ag space technology has actually done a lot. Could we do something more? Could we bring in water, energy, and so on? So this is a vision that came out of our workshop. We do have a lot of data. We heard about population is growing. A lot of us have seen the climate change. The temperatures are rising. Some of us also see the sea surface temperature, which allows us to predict El Nino and as well as predict the seasonality. But with this, could we actually even visualize the interactions? So here is a visualization from Google time lapse of the Central Asian lakes over 20 years with annual snapshots. And you can kind of see this lake disappearing. So there is no, I would say, really excuse. If you were monitoring a lot of surface water, you could start to see these trends. And not only that, if you actually study the context, you can see growth in cotton farms just upstream. And that's where the water of this river feeding the lake is being diverted. So this is one of the vision that, that came up from the workshop from data science angle. If we are able to at least monitor these resources, we would be able to avoid major disasters like this. Okay. So next, I'm going to talk about this Infuse workshops. And last year, NSF essentially started this initiative. And roughly mid-year, they gave out 17 workshop grants. And the idea was to engage many disciplines in this endeavor, including computing. And the basic premise was that even disciplines have been siloed. So people who study food, they are in one college or one place. People who study water, they have their own center. And energy is a third place, but there hasn't been enough effort to actually study the interactions. So that's why NSF wanted to have all the communities get ready, and essentially workshops were for partnerships and to identify new research questions. 2 workshops out of 17 had heavy size presence, including one from our side, and there was another one on more information fusion and CPS side. So just a glimpse of our workshop. It was hosted by NIFA and also co-organized by NIFA researchers. We had cross-sectoral participation as well as multidisciplinary. And we now have a revised report available for comments. And I have brought some paper copies if you are interested in looking at it. So this workshop here is showing some of the participants. At least a couple of them are here. Dr. Ramaswamy was the keynote. Thank you again. We also had, I see Vasant Honavar from CCC. He was there. And a few other people who are in the room. So here, we, in terms of outcome, based on different panel discussions and breakout and synthesis, I also saw Paul Gaither was in the workshop, right? Couple of things came out. One had to do with actually the data needs. And it turns out that if you look at the amount of available data, the food sector has been, I would say, the first one to realize the importance of the data. And they had ag census and other things. Energy sector did the same thing in mid-70s. But for water, we don't really have equivalent amount. And this is a data need that is there. I'm going to skip the other part. Of course, if you want to study the interaction, how much water is used for what purpose, we don't have a lot of data. The other part that came out was data science challenges. So it turns out a lot of data science, whether it is statistics, machine learning, or data mining, they have been developed for what I would call cyberspace. So they often don't think about laws of physics and other part of physical world, and that gives rise to many, many of these needs. So for example, we need tools to help people come to a consensus, because a lot of time water is constrained or land is constrained, and there are many stakeholders for different conflicting needs, and we need tools to help them come together. As I mentioned, a lot of data mining tools, they don't think about issues like spatial autocorrelation or heterogeneity or non-stationarity, and those have to be revisited. Same way, we often don't think about the physics-based causal models. So there is a big gap between all the correlations that we get from data science, and from there, how do we go to causal models, which is what a lot of physical scientists want. All right, so I'll just show you one example in a concrete way. So here is a geodesign tool, which is trying to decide how to use this piece of land, which is about 25,000 acres, divided into about 3,000 hydrological units. This is the current use is largely, as you can say, for conventional tillage and little bit of conservation, grassland and so on. And the idea is to change the land use to improve the energy and water impacts. When people get in a room and they work together, these are the kinds of design they come up with. And those have small benefits and small cost. Okay. You can run a linear programming optimization and come up with other designs, which give you a lot more benefit. However, none of the farmers actually like these designs. Okay. Can I ask you why? It's actually this part, the cost part can be subsidized. USDA has a lot of programs and so on, right? CRP and so on. That's not the issue, but what's the problem with farmers there? It's basically fragmented. You see these little pieces? So they would have to change equipment on the tractor every couple of minutes, and that's really a big hassle. Now, if you try to think about why is this happening, it's because most of our machine learning and linear programming, they are in a high-dimensional space, and they don't think about spatial neighborhood and spatial smoothness. And a lot of those things have to be revisited. A little bit of this we heard in the opening talk as well. Okay? So with this, I'll just go to the last slide and say that there is a lot of national interest on this topic. Since that, 2015, NSF came out with a solicitation this year, which was about $50 million. And next year, the amount is supposed to go up. There was another large conference in January. Midwest Big Data Hub with Clara's leadership is also setting up a group. There was a water summit in White House recently, and then security and so on. There are other events going on. So with this, I will pause here, and we'll wait for the questions.
Okay, thank you, Dr. Shekhar. Okay, and the final speaker will be virtual, and it will be Professor Murphy from Texas A&M. And are we queuing that up? I think they're working on it. I guess I have to improvise.
Computing can revolutionize economic and social resilience, how we predict, prepare, respond, and recover from disasters. It can save lives. It can reduce the long-term health impacts on survivors. It can reduce the economic consequences of a disaster while creating new jobs for veterans and preserving high-tech competitiveness. Disasters need critical real-time computing information systems. But of the hundreds of opportunities for scientific investment, why disasters? Because disasters actually aren't very rare, and they are very expensive. We get about 60 major federal disasters each year, and FEMA, just the direct cost to FEMA of the relief fund, is $7 billion. So to show how computing can make a difference, let me tell you a story about just one type of disaster, flooding, because flooding is the #1 disaster in the US and worldwide. And also economically, take a look at the National Flood Insurance Program, where we have $51 billion have been made in claims. It's already $24 billion in debt, and we know that more floods, more damage from land use and urbanization are on the way. But before I start the story about flooding, I just want to review the basic phases of a disaster. You have the prevention preparedness phases that occur before a disaster happens, and we're not talking about a climate change or any of that kind of, we're talking about a discrete event. And then after, we have the response and the recovery. Computing has already improved prevention and prediction. And if you think of all the modeling and supercomputing that we get from NOAA, from the Corps of Engineers, from the hazardous earthquake models, all of that is phenomenal. But supercomputing is only one type of computing, and it's only as good as the data it gets as input. And computing can also give you better input data in real time through innovations such as cyberphysical systems, flood gauges, unmanned aerial systems, and so on. So this is footage from one of our UAVs flying for Fort Bend, Texas, 2 weeks ago. It's one of the fastest growing suburbs of Houston. And so with the rapidly changing land use, they need overflights. They're getting them every 2 to 5 years, and that's just not enough. So when the rain began to fall up north, Fort Bend had access to great models for NOAA. But the problem was that the Corps of Engineers flood gauges weren't showing any change. Something was wrong. They could see the ditch was overflowing, but they couldn't see how far back the flooding went and how much land was being impacted and therefore would be saturated and flood the suburbs. And they didn't know that until we were able to fly a small UAV for them. Computing can optimize the response. And of course, there's lots of work in planning, logistics, the clever repurposing of business-to-business software to help compute what to deploy where, but also think about computing to help determine where the hot spots are, where most of the damage is. Now, one good thing about flooding is that it usually doesn't take down all the cell networks, which means that social media can be helpful. And one of our projects for an NSF research experience for undergraduates found that Twitter is actually a trustworthy indicator of the location and severity of flooding damage. So if you can get a hold of the Twitter feed for 4 hours, the first 4 hours of the event, and the tweet, it can be geolocated within 150 miles of the occurrence, it has pretty high value to civil engineers, public works, transportation engineers. What a wonderful finding. Computing can also start recovery sooner. And if computing speeds up the response, then the recovery can start earlier. Insurance adjusters can get into the site, the power companies can get into the sites and restore power, and that's going to help with resilience and economic recovery. But why are we waiting? It's information. Information can be shared. So as soon as the responders are getting the information, that information needs to be shared with Public Works, the County Road Commission, the insurance companies, and so on, so that they can get the job done. A large insurance company told me that if they can get a homeowner's claim processed 1 day early, it can make a difference of 6 months on getting home repairs. And the information isn't just pictures. This is a 3D reconstruction of the flooding at the Oso mudslides in Washington, and it has a 4-centimeter resolution. That's better than what you can get with a satellite. And it was taking the USGS 2 to 4 days to get a single build like this. With a UAV and the advances in computing chips, laptops, advanced processing speed, we're seeing 7 hours. Snohomish County was able to immediately start planning for flood control and to save the salmon fishing industry. But it's not all solved. One big problem is the size and volume of data, which is too high for cellular networks. Here's a Red Cross worker during the Louisiana floods taking a low-resolution snippet of UAV video to send to the Changapahoa Parish EOC by email. They didn't need the whole shot. They just needed a couple of snippets. The problem is we don't have data to decision models of who needs what when. There's security issues. There's modeling, social technical interactions, there's throughput, so much more to do. And all of those types of things that are needed to be done were outlined in our 2012 NSF CCC workshop. We brought together over 50 experts in 9 disciplines, and they all argue that disasters are indeed different, and they require a different dedicated focus on unique computing challenges. The emergency informatics domain is like healthcare. It's not just adding big data, but that's part of it. It's not just adding more cyberphysical systems, but that's part of it. It's not just taking advantage and wiring into smart cities, but that's part of it. It's not the Internet of Things, but that's part of it. That together part is what makes it unique and challenging, as well as the extreme amount of data, the extreme time pressure you have to make under these decisions. So, in conclusion, computing can save lives, increase resilience to disasters, preserve the quality of health and of livelihoods. It can reduce annual expenditures in our insurance deficit, and can create a new high-tech sector that will create new jobs in software, cyber-physical systems, high-performance computing, and telecommunications. Computing can do that, but it won't happen by accident.
Okay, thanks. So, let's see. So we can begin our sort of panel discussion, and I think we have Robin Murphy on the phone. Robin, can you hear me? Okay, we'll
Yes, I can.
Okay.
I just had to turn off the mute
No,
button.
that's great. Thanks. Okay, great, and thank you for your talk. And so so we can take questions from the audience if people would like, and otherwise I can start while people are thinking of their questions. Sonny, you had talked about this farmer, Dowdy, and George, I think it was, and it sounded great. And a lot of what we've heard this morning seems to be about integrating existing technologies in certain kinds of applications. And I'm wondering, what is that farmer, you gave a great story, but what's lacking? What is that technologically? What are the pieces missing? What does that farmer need next? What's the next step that's really in play here?
So, that's a great question, and if you look at a typical farm, it ends up having multiple different components to it. You'd think that the soil's an important part of it, of course, because you're going to have to plant the crops or raise the livestock on it. And then you've got the seed that goes into it, the seed that comes out, the water that's needed, the energy that's needed. And all of these things are different components, including the various types of pests that you've got, insects and pathogens and weeds and all that too. And what is lacking today is that farmer's ability to integrate all of that into usable approaches that he can go ahead and keep track of all the issues that are going on and come up with smart decision-making capabilities as well. It really comes down to that, is you've got unbelievable amounts of data that are coming down. In fact, I like to say that in addition to being an agronomist and a soil scientist and a hydrologist and an entomologist and all that, farmers are now data scientists as well. And being a data scientist really makes it very difficult to get all the data pulled together in a usable format. And I think that's the interfaces that need to be developed as well. And a lot of times, they're running around with handheld devices in their hands. And so the type of things that the prescriptive farming that I was referring to and that Shashi referred to as well, that Monsanto and other companies are selling, are really providing that sort of a service. And there's more and more data coming in, and so the better to be able to integrate all of that and come up with decision support tools. That's where the action's at.
So Shashi, and you talk about food, energy, water systems. Is that also an integration problem mostly, or are there other aspects as well?
So food, energy, water actually is a systems thinking, right? So it's not just the union of the three. So if we took all the knowledge we have about food and energy and water, and the same thing is true about computer science. If we just took our current machine learning and data mining and robotics and put it together, that still is going to miss the interconnections, right? So, so from the food perspective, for example, now there are a lot of regulations on farms about water quality. So we can tell them all about what's the best use of fertilizer to increase yield, but that would not help them comply with the water quality regulations. So you need to have additional knowledge about, if you put all the fertilizer in fall and 1/3 of that goes to the water, they will violate regulation. Right? So you need new knowledge. Same thing, if you think about like machine learning models or optimization models, if I'm applying it in physical world, they need to somehow, think about laws of physics, right? Which was in keynote speech as well. And it turns out that many assumptions in our machine learning and optimizations, they are not cognizant about laws of physics. You think about independence assumption. Data samples are drawn independently of each other, right? They all come from identical distribution. That does not happen in geographical data. So what you need is, it's more than the union. Okay? The whole is much greater than sum of its part. You need to look at interconnection. You need to think about, what do I do with physics? Carla mentioned you can put it as constraint, and that is great. But you could also put it in objective function, right? You could have a soft regularization, and that's a different thing. But it probably is also there in feature selection. So how do I put the two things together, right? Right now, data science gives me correlations. The physics-oriented people want causal model. How do I go from correlation to causal model? I don't believe we know that, and we need to do new computer science and research.
Greg?
So first, thanks for some great talks. It's really, really illuminating to see some of the spectrum of issues are up there. And in fact, that's one of the questions I had is, so if we actually look at both of the panels, the urban panel and this panel, there's this incredible spectrum of issues that clearly computing could have an impact in. And so I'm wondering, how do we actually create the on-ramps for the computing community to get involved? And in particular, in this area, I think it's more abstract for many of us. I'll bet almost everybody in this room lives in a city. And so when we talk about urban issues, they understand those issues. When you start to talk about a farmer fertilizing a field or driving a tractor, there's not many people here who have that experience. So how do we engage, particularly I think the younger generation of computing researchers, to actually be involved in this? I'd be curious for your thoughts.
All right. Well, thanks very much for that question. So I like to say that everybody has to eat. If you don't eat, you're toast. And everybody has to drink water. Everybody has to breathe in air. And these are the areas that we're deeply interested in, that every one of us needs to be interested in as well. So the on-ramp, from my perspective, my agencies, and NSF's perspective as well, the funding agency's perspective, is you can indeed provide us white papers, on our website and other places. We convene conversations. There will be a conversation that we're going to be convening in regards to data itself. And one of the names that you saw on Shashi's slides is a fellow named Parag Chitnis. He used to be with NSF until a couple of years ago. And he's going to be hosting this here. There'll be more information coming along as well. But rather than just waiting, if you've got some thoughts about what we can do, this community as a collective, for example, you might be able to provide us some white papers as well, because that'll go into informing us in regards to our budget narratives and funding priorities and things like that too. So that's one approach that I would encourage you to take.
Sure. So I will just add 2 cents. So already I think there are funding initiatives like Infuse. So that's already creating a atmosphere to encourage this kind of work. And I believe SAIS is putting up more than 20% of that money, so $13 million last year, which means there is an incentive. But I think the challenge for younger people is to form partnership. Many of them came out of PhD programs where they did not have partnerships with people in food, energy, water. And last year's workshops that NSF had, 17 of them were a start, but it's really a drop in the bucket. So we need to create opportunities for our younger people as well as the senior researchers to meet with other people in food, energy, water and form partnership. Because next RFP probably will come out in December. So probably this summer is a good time to start, and that's where the SIG-KDD workshop is in place.
I'd like to put it in perspective real quick. Yeah. So, NSF and NIFA, we partner on the Infuse initiative. But NIFA by itself, we're going to be this year, there's a whole bunch of RFAs coming out very soon in the food, energy, water, et cetera, systems. We're going to be investing about $250 million. And the data piece of it's a pretty significant part of it as well. Not all of it, but a significant part of it as well.
Okay, so
I'd like to just take an opportunity to jump in as well about the idea of on-ramp. Even though you think of food, energy, water being in urban areas, we're disconnected. We're also very disconnected from emergency response. And so one of the things that the 2012 study said, the number one thing to engage people would be to create these domain elucidation types of workshops where you can start forming those partnerships with the myriad agencies and industries, things like the insurance companies, the American Red Cross, not just the agencies such as FEMA, the state and local ones, to get them involved and to learn directly from them, from the different 15 emergency support functions. Also trying to reach out to the traditional conferences within the different aspects of computing to say, okay, you've got great theory, here's some things to do to apply it. Here's what these sets of problems and needs are. So I think, again, going back to the key thing for all of us is this need to create partnerships to allow our students, to encourage our students and young faculty to make these partnerships so that they can learn and contribute.
Thank you, Robin. Susan?
I'm Susan Graham from the University of California at Berkeley. A lot of what you've talked about in terms of food and water and also in disaster response is providing decision support for solving problems at the present time. If we look into the future and we think about climate change, then there are going to be changes that directly affect food and water and disaster, namely increases in temperature, changes in availability of water, and different climate patterns. And for example, people predict that crop production is going to move north in this country as the country warms. And what you're now producing in the southern U.S., you'll have to produce in the northern U.S. So that, too, seems to me like a rich opportunity for applying computing technology to plan for the future. The question is that happening? And what are some of the challenges that our community could be tackling?
Wow, thanks so much, Susan. I'll take that on first and give you my response, and then the others can join in as well. And absolutely. And so the last statement that you made about crop production will be moving north, it is happening right now. I'll give you an example of it. If I said corn production, more than likely people that know about food systems, they'll say Iowa is the center of the universe. Well, it turns out this past year was Minnesota. And a lot of the, and as we go further up north into Canada, they're picking up more and more of the acreage as well. And in fact, if you look at the impact of temperature, if you look at the impact of changing climate, the droughts, the availability of water based on current technology and all that, the World Resources Institute, you might want to look at some of the work that they've been doing here and presenting data on, predicts that if you just look at the United States, North America as a landmass, north from Minnesota on up north into Canada, you'll see a positive increase in yields and so on. And then south of there's a sort of an imaginary line almost, is going to be decreasing by very, very significant percentages. That's going to happen. So that's predicted to happen as well. So the data sciences, the kinds of things that you folks are into, and the expertise that you bring to us collectively, is those predictive, based on models and looking at what the temperatures are, what the water amount availability is. Again, taking into account today's technology, also predicting what the technologies might be in the next 5 years or 10 years or 20 years, because a lot of things that are happening in the world of desalination of water, there's lots of things happening on water use efficiency and things like that. But we don't have this sort of an integrative ability to bring all of those together and help us develop predictive models. That'd be something really critically important for us collectively.
So if I can add. Great. So this is, I think, really a great question. Food, energy, water, we can't just put a circle around that. It's affected by climate change, it's affected by population and rising economy. So in terms of climate change, I think there are two kinds of things which are happening, and certainly computing is involved in some of them. So one, which has been around for some time, trying to project future climate. So there are a lot of global climate models, and there is consensus. In fact, within computing community, there is an expedition on understanding climate change using data-driven approach, which is at Minnesota is part of that. Now, its effect on agriculture, also now there is a community called AgMIP, Agriculture Model Intercomparison Project. And what they are essentially doing is to look at different stages of a plant growth and effect of rising temperature or increasing standard deviation in precipitation on the plant. So there are many, I think, several models that look at that stages. Using the insights from that, one could try to think about how to intervene in terms of either irrigation or fertilizer. But it also tells us what would happen to the yield in different climatic zones. So these are, again, very simulation-based projects. And certainly when it comes to simulation, at least from cyber infrastructure perspective, computing is heavily involved. Right? And people are also looking at the patterns in precipitation. So that's where climate projections are not as robust as temperature. But certainly for policy making and so on, people are at least looking at some of that. In precipitation, one of the trends they are seeing is that the standard deviation is going up, right? So you have very heavy rainfall for a short period and longer period of drought. And that's another place one can start being creative about what are the solutions. So some farms which are not, which don't have canals and pumps, they are putting water retention ponds. And now suddenly it's back to the optimization problem that Carla and I might talking about. So you have a finite piece of land. Some of that now has to be used as a water retention pond. Or you may have to put a little bit more drainage when you have heavy rainfall, right? So a lot of, I think, the core optimization, the core machine learning, those problems come back to this, but the context starts to shift. But from, I would say, machine learning perspective, a huge issue is non-stationarity, and you kind of just illustrated it in the most beautiful manner. We can look at all the past history and learn the model, but if the climate is changing, it's all non-stationarity, right? How am I going to take this model forward? So now our machine learning has to somehow work with simulations together and come to something more interesting.
That's good, thanks. And Robin?
And I
Yeah.
would certainly agree. That whole idea of the modeling and simulation is so critical. Machine learning, like you're saying, for just the static cases. What drives me nuts is that you get new data from a flood, and it takes 7 years to get integrated into our current modeling and simulations of additional flooding. So those are some of the places where computing can really help, not only getting more data, more accurate, comprehensive, minute-by-minute data of what's happening well before a flood, how the land use is changing, how the elevations are changing, but also to update those simulations and models in real time, check to see whether they're working and have them upgraded.
Great. So Robin's comment, I just want to add one more thing. Another big change is the extreme events in climate, right? Their frequency is changing, their magnitude are changing. All our infrastructure used to be designed on 100-year floods. Now that 100-year flood is completely different animal. And it turns out that the machine learning statistics that we can use for average data doesn't work well for extremes. And you need to go to heavy tails and a lot of stuff goes on there.
We're going to have time for just one more question, I'm told. So.
Vijay Narayanan from Penn State. How much of the decisions are actually limited by the data that's available as opposed to political decisions, public policy, and other types of pressures? For example, the RLC aspect that you showed, I think I've seen this image of shrinkage for the past 15 years, but then there is this immediacy of we want to be the world's largest cotton producer right now, so they don't really think about this. Yeah. And then if I really think about some data from water sources being drained from underwater depletion in places like India, we know that it's being depleted, but I have no other source of water to drink right now. So am I really going to look at your long-term models and data, or am I really going to look at the water that I have to drink today? So how much is really data? How much can we really change? How can we actually go away from immediacy of solution, be it for political policy making or people really in poverty looking at what is on their plate as opposed to the global good or other things. Can you please comment on it?
Yeah, if I could. So I skipped several slides towards the end because I saw the sign saying I only had 2 minutes. The very last slide of my presentation had 2 words on it: humans matter. And ultimately, it's humans that make decisions. And to your point, if we don't have the political will and the appropriate policies and regulations and all that, all the greatest, fantastic, most fantastic data analyses, models and all that mean nothing at all, because people are going to, use the water in any which way they can and things like that. And so it's really incumbent on all of us collectively to get people along as well in helping make decisions and things like that. And there's a disconnect. So the biologists run in their own way, the physical scientists run in their own way, the data scientists run in a different direction altogether. Bringing it all together, but bringing the people along as well is really, really important. And so the sociological aspect, the social sciences, regulations and policies, critically important. And we don't do enough of a good job to help bring that. Again, we made a conscious decision here, my agency, NIFA, and we're partnering it with the social science parts of SBE, Social Behavioral and Economic Science of NSF, to help provide funding for those sorts of things as well, that the social sciences need to come along.
So I would just like to add the following. Science is an input to social decision making and policy making. So even looking at India, they are water constrained. Certainly this is a very tough year with drought. But one could ask, are there options that they could, consider? So for example, there is a notion called virtual water trade. And they are saying, well, if India needs water for drinking, maybe some of the agricultural crops may be changed, right? They could import cotton because that's very water hungry. But again, at the end, it has to be a policy decision by the politicians, and the public has to be informed. But what we can do is to at least provide the information. Science could probably say, here are some new ways to look at it. But ultimately, the policy decision is with policymaker, and somebody in that space has to take the lead and bring the public along to make tough decisions.
Okay, so with that, why don't we conclude our morning session? Thanks for all the speakers and for all of you for the great questions.